Hi, my name is Oktay. Welcome to today's video about the chemical element selenium. And this is a picture of the element selenium. It has the atomic number 34. Its name comes from the Greek word Selene, which is a Greek goddess of the moon. Gray selenium is the most stable of several allotropes. Allotropes are different forms of the same chemical element. In nature, there are 7 isotopes of selenium. The most common is the selenium isotope 80. Second is selenium 78. And 2 of the isotopes are radioactive. Selenium 82 has a half-life of 9 times 10 to the 19 years. And selenium 79 has a half-life of 327,000. This is a picture of the nucleosynthesis of the origin of the chemical elements. Selenium is a member of the chalcogene group here. It is produced in exploding massive stars and is an essential trace element. The recommended daily allowance is about 60 to 70 micrograms per day. And in higher doses, this element selenium is toxic. This is a picture of the abundance of the chemical elements in Earth's crust. The y-axis is logarithmic. And you can see here, selenium is here. It's a very rare element. The average soil concentration is 0.4 milligrams per kilogram. And the human body contains just 13 to 20 milligrams of selenium. Selenium was discovered in 1817 by Jöns Jakob Berzelius, that's the gentleman at the left, and Johann Gottlieb Gahn, the man at the right. They found it in a red precipitate of the lead chamber process, which is the process to make sulfuric acid, H2SO4. And this red precipitate contains selenium molecules, for example, the molecule SE8. These are 3 allotropes of selenium. At the left, that's the black selenium. In the middle, that's gray selenium, that is the most stable allotrope, and it is a semiconductor. And at the right, that's red selenium. These are a few examples of selenium minerals. At the left, that's selenium in sandstone from New Mexico, USA. In the middle, that's chalcomenite from Bolivia, which is copper selenite dihydrate. And at the right, that's schmiederite from Bolivia, which is lead, copper, selenite hydroxide. This is a picture of black selenium. The world selenium production in 2020 was 3,300 tons. Number 1 producer is China with 1,120 tons. Number 2 is Japan. Number 3 is Germany. And selenium is isolated from the byproduct of the copper and nickel production because it is in the anode mud. And this is a chemical reaction how to isolate selenium. That's a reduction of selenous acid with sulfur dioxide. That makes selenium and sulfuric acid. Next step is purification by vacuum distillation at 280 degrees Celsius. This is one of the applications of selenium. This is a rectifier, which is a device for converting AC, that's alternating current, to DC, that's direct current. Nowadays, selenium is replaced by silicon-based rectifiers. Other applications are for fertilizers, for the purification of the element manganese. In the glass industry, you can make red glass. And for alloys. In alloys, selenium gives alloys strength and corrosion and wear resistance. This is a picture of how the laser printer is built. The photoconductor drum, that's here. This part is in laser printers and copy machines is coated with selenium. This gives you a higher quality and consistent prints. This is a picture of CIGS, a solar cell. CIGS is copper, indium, gallium selenide. This type of solar cells have a maximum efficiency of about 22%. And this is a thin film technology. Yes, this compound is more expensive than silicon, but since it's a thin film technology, you need just a layer of 1 to 2 micrometers. That's typically about 1/100th of a silicon-based solar cell. This is a picture of the development of in a solar cell technology over the years. X-axis is a year, y-axis is cell efficiency. And you can see the CIGS solar cell is in green circles here, about 22-23% efficiency. That's the same level as silicon solar cells. Another alternative is cadmium telluride. This here, also at about at the same level. And another alternative is perovskite solar cell, where the perovskite solar cell is not fully developed yet. This is a picture of zinc selenide, ZNSE, that's used in transparent glass and visible and infrared light. The first blue LED was based on zinc selenide and was later replaced by gallium nitride, GaN. This at the left is a picture of selenium dioxide, SeO2. At the top right, you can see it's a polymer structure. At the bottom, there's one of the uses for selenium dioxide. That's the Riley oxidation, was invented by Harry Lister Riley in 1932. That's a selective mild oxidation of alkenes or ketones. In this example, that's a diketone, and you can make this oxidation reaction with selenium dioxide, which is reduced to selenium, and you get this alkene. A picture of bluing of steel with selenium dioxide. It gives a partial protection against rust. You can make a thin 1 micrometer black oxide layer. This black oxide layer consists of a 1-to-1 mix of iron 2 oxide and iron 3 oxide. This is an electron microscope image of selenium nanoparticles that were ejected by laser ablation from a bulk selenium target in distilled water. And these nanoparticles have a potential for cancer therapy. And this research is at early stage nowadays. This is a picture of the selenium cycle in nature. You can see there are two intermediate products, that's DMSE and DMDSE. That's dimethyl selenide and dimethyl diselenide. And you can also see in the nature, there can be the redox reactions can go in both directions. You can have an oxidation and a reduction. And you can see that selenium oxide particles can be transported through air. This is an example of selenium in food. One example is garlic, but also nuts, cereals, meat, liver, mushrooms, fish, milk, and eggs. All these foods contain the element selenium. In biology, selenium is a very important trace element. For example, it is needed for the thyroid hormones. You can check my iodine video if you're interested in how this works. Selenium is a part of the activation of the T4 thyroxine hormone, but it's also important for the peroxidase and the dehydrogenase enzymes. This is a picture of L-selenocysteine. At the left, that's chemical structure. You have here a carbon atom with 4 different groups. One hydrogen, then this group, this group, this group. So this is called a chirality. You have a carbon atom with 4 different groups in a tetrahedron structure. There are 2 versions of this molecule, the L and D version. It's like a left hand and right hand. The L version is important for the synthesis of peptides and proteins. And the D amino acids are also important because they're the building blocks of the bacteria. The human body contains far more bacteria and microorganisms than cells. And that's why the D amino acids are also important. And one important source for D amino acids is yogurt. So in the human genome, there are 25 selenoproteins encoded. It is the building block of several enzymes, for example, antioxidants. And there's also a methionine analog of L-selenomethionine, where sulfur is replaced by the element selenium. This is a picture of chalcomenite, which is copper selenite dihydrate from Bolivia. And this is a picture of selenium crystals in a uranium deposit. This is a picture from Germany. And that was today's video about the chemical element selenium. Thank you for watching. Have a nice day. Bye-bye.